Okay, so good afternoon. Welcome to the afternoon session. And let me introduce the next speaker. So it's my great pleasure to introduce Jérémie Szeftel from Sorbonne Université. We'll talk on nonlinear stability of Kerr for small angular momentum.
Okay. Thank you. Thank you very much for the introduction, and I'd like also to thank the organizers to invite me here. Okay, so I will start with a brief introduction to the main equations I'm going to consider, which are Einstein equations in a vacuum. So my main object will always be a Lorentzian manifold Mg. So here M is my manifold. It will always have dimension 4, 1 for time and 3 for space. So this is the physical dimension. And the Lorentzian metric G will have signature minus, plus, plus, plus. And of course, the simplest example of such metric is the Minkowski metric, which is the flat case in Lorentzian geometry. So the manifold M is R1 plus 3. And the Minkowski metric in Cartesian coordinates is given by minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. Okay, so here this equation is an equation on the curvature of my Lorentzian manifold. So Minkowski is the flat case, and I need an object to measure the curvature, and this object which will be the so-called Riemann curvature tensor. So it's a 4 tensor, it has 4 indices, and this contains all the information that you want on your manifold. And in some sense, if you want, given that Minkowski is the flat case, the curvature tensor somehow measures the distance to the Minkowski spacetime. Okay, and this curvature tensor, you can contract 2 indices. You can take a kind of trace, in which case, if you contract the third and the first and the third index, then you get a symmetric 2 tensor called the Ricci tensor, which has only partial information on the curvature. And the Einstein equations in the vacuum simply correspond to Lorentzian manifolds with a vanishing Ricci tensor. Okay, so these are the equations I'm going to focus on. And these equations in particular have a special property. Here is the first property of these equations, is the one of general covariance. If I have a metric solution to Einstein vacuum equation, and if I pull back the metric with any diffeomorphism, then I still get a solution of the Einstein vacuum equations. And for this reason, you want to consider, in fact, that these two metrics are in fact reflect the same solution. So in fact, you don't look at just solutions of Einstein vacuum equations, but rather class of equivalence of solutions modulo diffeomorphism. Okay, so this is the so-called principle of general covariance. If you want another way, so this will play an important role in this talk, but another way to look at general covariance is the fact that these equations are invariant under change of coordinates. So the Einstein vacuum equations are true in any coordinate system. You have the freedom to pick your favorite coordinate system. Oh, sorry. Okay, so now let's talk about the nature of these equations. So these equations form an evolution problem. In other words, if you look in specific coordinates, you will see some hyperbolic equations, for instance, of systems of wave equations, if you want. And in particular, because it's an evolution problem, you have to set up the initial value problem. So here, it's not too important for me, but just for reference, you can set up these initial data sets for Einstein vacuum equations as a triplet given by a three-dimensional manifold, a Riemannian metric G0 on sigma, and a symmetric 2 tensor K again on sigma. And these have to satisfy some compatibility conditions known as constraints equations, which is a geometric system of elliptic partial differential equations. But I'm not going to write it down because it's not going to play a role. The only important thing to remember is that this is an evolution problem. So if I give you suitable initial data, then there exists a unique maximal solutions to Einstein vacuum equations. And these maximal solutions are usually called globally hyperbolic developments. Okay? So the statement of existence and uniqueness is the seminal work of Yvonne Choquebrua. That somehow started the field of mathematical general relativity. And the statement of the notion of maximal solution, because of general covariance, is a bit more subtle. And this is due to the work of Yvonne Choquebrua and Gerrosh. Okay, so once you have this statement of existence of maximal solutions, let me also mention important particular cases which are stationary solutions. You always want to look at stationary solutions because they might be the end state of the evolution. So here we have seen already one stationary solution, that's the Minkowski spacetime, that's the flat spacetime. And the solutions which I will be interested here are in fact Kerr black holes, which is a two-parameter family of solution which I will introduce later. But for now, let's just assume that these are important explicit stationary solutions of my equations. Okay, so to start the discussion and to motivate what I'm going to say, I want to present really a central conjecture which you should think of as really a very long-term goal, which is a motivation somehow for the entire field of mathematical GR, and that's the so-called final state conjecture. And it answers the following question: what happens asymptotically to these maximal developments? In other words, Choquet-Brouillard-Guéroche associate to any initial data a maximal development. I want to understand what happens asymptotically, in other words, for very large time. Of course, time is a dubious notion in general relativity, so take time in quotes. So here is the conjecture. The conjecture says that if I take a generic initial data set, this will lead to a solution which behaves in the large like a finite number of Kerr black holes moving away from each other plus a part that decays to zero. So in other words, you have at the end, if you wait sufficiently long, you will see these Kerr black holes and they will just move away from each other and the rest will just disappear, okay? So this is, of course, what this tells you is that in general, what you should expect, of course, is that there is a very complicated transitory regime. In this transitory regime, at first, you expect that black hole will form, that they will interact, that they will possibly merge, and in fact, black hole merger is the main source of gravitational waves that has been observed so far by the gravitational waves observers such that Virgo and LIGO. But what happens is that there will be a striking asymptotic simplification of the dynamic. If you wait sufficiently long, this complicated transitory regime will disappear, and asymptotically, you will have this very simple description according to this conjecture. Okay? So this is, in fact, this is a conjecture which is also believed to be true for many other equations, evolution PDE, and usually in other contexts, it's called the soliton resolution conjecture. So here, my solitons are the Kerr black holes. Okay, so again, this is a very long-term goal, and I wanted this to state this just as a motivation. So let me give you three conjectures which somehow are necessary conditions for this conjecture to be true and which are more tractable. So let me mention these three problems. The first problem is the one of collapse. So somehow the final state conjecture expects that black hole will form. So there is already the first question, can black hole indeed form? If I give you a reasonable initial condition with no black hole, will they form dynamically? So this is in fact a question that goes back to the seminal work of Roger Penrose from '65 and his concept of trap surfaces. And this has been revived after the breakthrough work of Christodoulou, which indeed showed that this collapse is possible. He showed formation of black holes, and there were lots of subsequent works, and I expect that there will be many works in that direction. Then there is the question of rigidity. The conjecture tells you that any dynamical black hole will end up being a Kerr black hole. So this is really the question of classification of all possible stationary vacuum black holes. This conjecture assumes that any black hole any stationary black hole has to be part of this Kerr family of solutions. So this type of questions go back to the seminal work of Carter, Robinson, and Hawking, who answered this question positively in the analytic class, and this has been revived recently in the wake of the work of Ionesco and Kleinemann and subsequent works in the smooth class. And in the smooth class, this is still an unanswered question. It's still not known. There are partial results, but no definitive answer. And finally, there is a third question, which obviously is a necessary condition for this conjecture to be true. If any data is to become a Kerr black hole, what about data that start arbitrarily small? So what about arbitrary small perturbations of the Kerr family? Are these arbitrary small perturbations, do they stay globally close to Kerr and do they reconverge to Kerr? This is the question of asymptotic stability, and this is the question I'm going to focus from now on in this talk. Okay, so from now on, I'll just mention the third question about stability. But first of all, now that I talked a lot about the Kerr solution, let me just present you what is the Kerr family of metrics. Okay, so I'll spend 2 slides on explaining what they are. And let me start just with a formula. So you can actually write a formula down. So the Kerr matrix, here I will give them in Boyle-Lindquist coordinates. By general covariance, I could choose any coordinate system. I want to choose this very simple one, which are these TR theta phi spherical coordinates of R1 plus 3. And in these coordinates, you get this formula, which is quite complicated, but fortunately completely irrelevant here. The only relevant thing is that you have an explicit formula. So it's an explicit family of solutions to Einstein vacuum equations. Second observation, this is a 2-parameter family of solution. You have a mass parameter, it's indexed by a mass parameter M and an angular momentum parameter A. Okay? And third observation, if you look at the metric coefficients, even though they are quite complicated, they are only functions of R and theta coordinate. They do not depend on the T coordinate and the phi coordinate, which means that these are stationary solutions and they are axisymmetric. Okay? In fact, there was an earlier family found before, which is the Schwarzschild family. And the Schwarzschild family turns out simply to be a particular case of the Kerr family when you take the angular momentum to be 0. And in that case, the solution is even more symmetric. It's in fact spherically symmetric. And the formula is much simpler. It reduces to this simple formula here. Okay? So this formula is also not too relevant for the talk, except for the 2 simple observations I'm going to make now. So if you look at the coefficients in front of dt squared and dr squared, I'm only going to focus on these 2 coefficients. And if you let the special coordinate r go to infinity, then obviously this coefficient goes to -1 and this one goes to +1. And you can recognize the Minkowski metric written in spherical coordinates. Okay, so this means that these metrics are all asymptotically flat. That means that they converge to Minkowski at special infinity. Okay? And second observation, there seems to be a singularity at r is equal to 2m. So this, in fact, is not a true singularity. So in general relativity, you always want to distinguish true singularity for coordinate singularity. So this is, in fact, a coordinate singularity because I can change coordinates and remove the singularity. However, it still indicates that something special happens at r is equal to 2m. Okay, so what happens is, in fact, the main property of this spacetime is the fact that they contain a black hole. So the Schwarzschild spacetime corresponds to non-rotating black holes, while the Kerr spacetime corresponds to the general case of rotating black holes. And here you have to restrict to the physical restriction, which is that absolute value of the angular momentum has to be less than the mass. Okay, so maybe let me explain in simple words what it means to be a black hole. And for this, I will restrict to Schwarzschild. The case of Kerr would be analogous, but Schwarzschild is a bit simpler to explain. Okay, so here, for simplicity, I will draw things in RT coordinates, and because Schwarzschild is spherically symmetric, it means that any point here on this diagram is in fact a round-to sphere. Okay, and to understand the structure of the Schwarzschild spacetime, I'm simply going to draw light cones and look at their form. So this is called the causal. You want to look at the causal structure of your spacetime. So I will start with a far away region when R is very large. So when R is very large, it's asymptotically flat, so you expect that your light cones will look like the ones of Minkowski. Okay, so these are your familiar light cones. And then when R decreases, your light cone is going to be more and more deformed because you drift further away from Minkowski, up to the time when you reach this special hypersurface R is equal to 2m, so that your light cone, in fact, is tangent to it. Okay, so this is exactly what it means to be a black hole. If you look at the trajectory of lights, which are the generators of this light cone, if you want, these are the null generators or the null geodesics that are spanned by this light cone, they all point inside this region R is less than 2m. So light cannot escape from that region, and that's exactly what it means to be a black hole. So the black hole here will be R is strictly less than 2m, and R is equal to 2m is called the event horizon, is the limit of what we can see us as outside observers. Of course, we think of ourselves as being outside of the black hole. So if you're outside, the region you can see ends up at this event horizon, hence the name horizon. Okay, so now that I have presented the Schwarzschild on the Kerr black hole, let me finally state the conjecture I want to consider, which is the Kerr stability conjecture. So let me remind you that we are in the context of asymptotically flat solutions to Einstein vacuum equations. And in this context, we have the following conjecture. So first of all, it's not the conjecture of the stability of the entire solution, but only of the exterior region. So the exterior region is the region outside of the black hole. In fact, the inside of the Kerr black hole is expected, on the other hand, to be unstable. So that's why we have to focus on the exterior region. And the conjecture is that if you start with small perturbations of initial condition of an exterior Kerr solution in the so-called subextremal restriction, in other words, the absolute value of the angular momentum is strictly less than the mass, then the corresponding solution, the corresponding maximal development is global. So the solution is global, it stays globally close to Kerr, and it converges asymptotically to another member of the Kerr family. In other words, you should expect that in general, it's not the stability of one solution, it's the stability of a two-parameter family of solutions. So in the limit, you will converge to a different member of the Kerr family, and tracking the final mass and the final angular momentum is an integral part of understanding this conjecture. Okay, and maybe let me talk about a related result, which is the seminal work of Christodoulou and Kleinemann, which is the first stability result in the field, which is the stability of the Minkowski spacetime. And in other words, this is the stability of the flat solution. So here the link is that now this is a conjecture for the stability of more complicated solutions, namely Kerr black holes. Okay, so what I want to do from now on is explain the history of this problem, starting with the physics literature. And then I will mention a recent resolution of this problem for slowly rotating Kerr black holes. And hopefully I will have the time to discuss maybe some aspects of the proof. So let me start with the history, and let me start with, in fact, the physics literature, who studied the so-called linearized gravity system. So what is the linearized gravity system? Well, I'm going to assume the result to be true, and I'm going to decompose my perturbation of Kerr as a Kerr solution. So of course here already I'm simplifying the problem because I'm, in reality I will converge to a different Kerr, but let me forget about this issue. So I want to decompose my metric, my general metric as a Kerr metric plus a small perturbation. So here H would be a symmetric to tensor small in some norm, suitable topology. Okay, and then I want, instead of looking at the full problem, I'm going to expand the Ricci tensor. So I can expand the Ricci tensor, and I will plug my decomposition and expand the Ricci tensor as follows. So I have the Ricci of my metric. So this is 0. This is what I'm looking. And then I can expand. I can say that this is the Ricci at Kerr, which itself is 0. And then I have a first order term, which is the variation of the Ricci tensor at the Kerr metric applied to my perturbation H. And then, of course, I have higher order term. Let me symbolically denote them by HD2H plus the H square, which is what you would see in a generic coordinate system. So the simplest problem is simply to suppress this problem, which, of course, is a very important part of your problem, and to just look at the model problem, at the linearized model problem, which is the one written on top of my slide. In other words, I just keep the first order perturbation. Okay, so this is called the linearized gravity system. So in other words, it's just the linearized equation around Kerr. And there is a huge physics literature that was devoted exactly to understanding this problem. And you should understand that for this toy model problem, stability of the true Einstein equations means looking at this toy model problem and proving decay. And you expect that this will lead for interesting information to the true problem, on the true problem. Okay, so this started with the work of Roger Wheeler in the 50s and spanned up to the work of Whiting in the 90s. And here I'm mentioning also along the way the work of Tukowski and Chandrasekhar. In fact, there is a huge physics literature, and I'm mentioning here the particular references that will be important for the talk. Okay, so let me draw an analogy with the simpler problem of the stability of Minkowski. So if you were in the context of stability of Minkowski, in other words, the flat solution, you could again look at what it means to be solution to this toy model problem. And in this case, what happens is that the Minkowski solution is very simple, and this induces, this is a priori a large system of equations, coupled system of equations, but in Minkowski it totally decouples, and you are just left with understanding one wave equation. Okay, so this is to give you a sense, of course, that this toy model problem is much simpler than the true problem, simply because for the true problem, I mean, for this, for this problem here, understanding the decay of linear waves on Minkowski is one page in any classical textbook, while understanding stability of Minkowski took 500 pages to resolve. Okay, so clearly this is a very simplified Tory-Murray problem. However, in the case of Kerr, even if it's a simplified Tory-Murray problem, it's still highly non-trivial precisely because there is no disentanglement. This is still a large and entangled system. So let me explain what has been done in the physics literature to approach this problem. And I want to, in particular, focus on the work of Tucholsky. And the idea of Tucholsky was, in fact, very simple. In essence, you want to draw an analogy with what you would do with your favorite linear system. So let's say that you want to solve a linear system. If you want to solve a linear system, so think, of course, here it's a coupled system of PDEs, of partial differential equations of hyperbolic type. So it's certainly much more complicated. But if I had a linear system, and coupled system would mean that my matrix is full. And obviously, if you have a full matrix, what you want to do, obviously, is you use your favorite method to solve a linear system, which I'm going to take my matrix and apply Gauss method to put it in lower triangular form. Okay. And if you do this, then of course you want to start from the top and solve your linear system from the top to the bottom, one component after another. And if you want to do this, obviously the Gauss method starts with finding one component that totally decouples from the rest of the linear system. So this is exactly the idea that Tucholsky applied for the linearized Einstein equation. Of course, the difference in the work of Tucholsky is that the linearized system is a coupled system of hyperbolic PDEs, and in general, there is absolutely no reason why this should be true. In general, in fact, you cannot do this. But here there is an algebraic miracle, which is a combination of the fact that these are Einstein vacuum equations and that you are dealing with a Kerr solution. And he could exhibit such a quantity, which turns out to live at the level of curvature tensor. In fact, this is a very special contraction of the curvature tensor with certain null directions called principal null directions. And in that case, you find, in fact, you could not find, in fact, one quantity, but two quantities, which I'm going to denote for simplicity, psi plus and psi minus, that satisfy the so-called Tucholsky wave equations, which are so-called spin-2 waves. And these spin-2 waves, they consist of the wave operator on the Kerr metric plus first order and zero order terms. And they have, by themselves, they are complicated in particular due to these first order terms in red. These first order terms are responsible for the fact that these equations do not derive from a Lagrangian. And this comes with its own sets of difficulties. So this is unlike, of course, the scalar wave, which is a so-called spin zero wave. But if I forget about this issue for one moment, the goal is pretty clear. You want to first derive decay for Tucholsky based on these Tucholsky equations, and you want to rely on it to derive decay for the rest of your coupled system by exhibiting a triangular structure very much like the Gauss method for linear systems. Okay, and of course, if you want to have a chance to start this problem, you first need to understand the decay of Tucholsky. So I want to spend 2 slides on the decay of Tucholsky equation. And in particular, before even mentioning Tucholsky, you want to look even at the simpler problem where you don't have these terms in red and the potential here, and you just look at the scalar waves, which are the so-called spin zero waves. So let me spend 1 slide on the scalar wave, and I want to explain the role of geometry here. I want to explain why understanding decay of linear waves means understanding well what aspects of the Kerr geometry will affect the decay of waves. So there are 4 geometric informations that are important here. The first one is, so there are 2 good news if you want, and 2 bad news and then 2 good news, and this is why the 2 good news somehow will be enough to counterbalance the bad news. So the 2 bad news are as follows. So first of all, there is presence of trapped null geodesics. So trapped null geodesics are geodesics which escape neither to infinity nor inside the black hole. So this is a bad news because simply decay for linear waves results from the fact precisely that waves escape either inside the black hole, either to infinity or inside the black hole. And this is precisely what trapped null geodesics don't do. And you expect, in fact, that wave equations at high frequency will localize along null geodesics. So these trapped null geodesics are pretty problematic. Fortunately here, the good news is that the trap-link is fairly weak. It's called hyperbolic. And for this reason, in other words, it's unstable, and that's why you can still do it. But you have to deal with this issue. Another issue you have to deal with is superradiance. Superradiance is the fact that you do have a killing field because Kerr is stationary, and this will induce, by Noether's theorem, this will induce a conserved quantity. And usually in Minkowski, the analog in Minkowski will give you a positive, coercive quantity, so a global positive quantity. But in Kerr, because the time-lag vector field is only, the vector field dt is time-lag only for large R, your conserved quantity is only positive for large R, but not for small r. And this is another problem if you want to rely on this energy type method. Now let me come to the good news. So the good news is, on one hand, this redshift region. So the redshift region takes its name from the physical phenomenon of the redshift near the black hole. It's a small neighborhood near the black hole event horizon of the black hole, where you have good properties from point of view of decay of linear waves. And finally, the other good news is the large R region, because you are asymptotically flat. Kerr looks like Minkowski, which of course is the case that you understand best. Okay, so somehow the idea is that the two last points are counterbalancing the difficulties that you have, and they can still prove decay. And in fact, this was done in this series of work here, starting from 2003 to 2014. So it took 10 years to really completely settle this question of decay of linear waves on Kerr. And this was, of course, an important achievement of the field. So this is what I wanted to say on linear waves. Now let me come back to Tucholsky, which I recall are spin 2 equations. So they are more complicated. And the first, in fact, the physics literature, this is the last result I'm quoting, is the one of Whiting, could prove that these Tucholsky equations have no exponentially growing modes. So if you want, so this is in fact very far from what you want to achieve. You really want to prove quantitative decay rates for solutions if you want to apply it to the true problem of Einstein equations. But at least if you want, you should understand the result of Whiting as saying that there are no obvious counterexamples to decay. Okay? Then, of course, you still have to prove decay, and the difficulty of the result of Whiting is due, as I mentioned earlier, that the Tucholsky equations do not derive from a Lagrangian. However, there is the work of Chandrasekhar that tells you that there is a special transform that will send solutions to Tucholsky to solutions to Regge-Wheeler, which is another wave-type equation, but this equation is much better because it does derive from Lagrangian, and therefore you can hope to import the technology for the scalar wave to the solutions of Regge-Wheeler. And this is in fact what you do, and this was the key idea in the work of Dafemo-Solzhenitsyn that proved decay of Tucholsky on Schwarzschild, in other words, Kerr for zero angular momentum, and then this was extended to the full, very recently, to the first to the small angular case, and then to the full sub-external case recently. Okay, so this was what I wanted to explain for the decay of Tucholsky, and now let me spend one slide to come back to the decay of the full system, which is the linearized system. Recall that Tucholsky is a subsystem. Now I want to go back to the full linearized system, so the first toy model I mentioned. And here I want to say that in fact you cannot fully solve that problem. And the reason why you cannot fully solve that problem is that due to the presence of a kernel, and the presence of this kernel is in fact very classical. It should not be surprising, sorry. Well, okay. The presence of this kernel is due to the fact that simply you are not looking at one stability of one solutions, but rather a multi-parameter family of solutions. We have seen already two parameters, A and M. And of course, there are infinitely many extra parameters because you can pull back by any diffeomorphism and you get again a solution to Einstein vacuum equations. So if you use this and you take the variation with respect to any of these parameters, because it's a smooth multi-parameter family, it is classical to show that all variations with respect to any of the parameters will end up in the kernel. Okay? So here you have two parts in your kernel. You have a finite dimensional kernel, which is the variation with respect to the mass and angular momentum, and you have an infinite dimensional kernel, which is in fact due to the general covariance, so the diffeomorphism invariance of the equations. And this has the dimension, is the Lie derivative of any of the Kerr matrix with respect to any vector field. So it has the dimension of all vector fields in R4, and therefore it has infinite dimensions. Okay, so of course you could ask yourself, well, so the fact that there is a kernel, if you take my analogy with a matrix, with solving linear systems, obviously means that you are not going to be able to fully solve this problem. You can only solve it up to the kernel and the co-kernel of your matrix, if you want. So here it's the same thing. You have to be orthogonal to the kernel and the co-kernel if you want to solve this linear system. But on the other hand, at the nonlinear level, for the true Einstein equations, as I explained, you expect to have stability. So what happens is that at the nonlinear level, this kernel, in fact, simply means that you will have to track the change in the mass, the angular momentum, and the diffeomorphism, or if you want, you will have to track what are the final mass, angular momentum, and diffeomorphism in your evolution. So it's the fact that this parameter change, which is reflected in the kernel at the linearized level, and usually tracking this at the nonlinear level is what is referred to as modulation theory. And the important aspect in this particular proof is that the kernel, usually modulation theory is done in finite dimension. So this is a typical method in dynamical system that is what you use in Hamiltonian PDEs. But the difference here is that, contrary to usual, here you have, due to general covariance, you have to deal with modulation in infinite dimensions. And this is an interesting part of the problem, which hopefully I can discuss later. Okay, and finally, let me mention that, bearing in mind that there are these obstructions, the decay for the linear relative system was obtained, and in fact the current state of the art is that it's known for slowly rotating Kerr black holes. Okay, so this is what I wanted to say about the history of this problem, and now I want to come, so this was I wanted to explain simple ideas on a toy model problem, and now I want to come back to the true problem, in other words, the conjecture, and I want to present this stability result for this nonlinear stability. So it's if you want, it's the resolution of the conjecture for slowly rotating Kerr black holes. Okay, so if you have slowly rotating Kerr black holes, the conjecture is true. These are recent joint results with Sergio Kleinerman, my student Daiwei Shen, and Elena Jeudi. And there are several parts in this work, so let me maybe single out each part. So there is an important part devoted to this modulation procedure in infinite dimension that I mentioned earlier. So these are joint work with Sergio Kleinerman and a work of my PhD student Daiwei Shen. And then there is a work that has to do with the gauge constructions. You have to make gauge choices and construct them, and which deals with all decay estimates except for the Tucholsky scalars. This is joint work with Sergio Kleinerman. And the most recent work that completes this program is joint work with Elena Jeudi and Sergio Kleinerman. So here there are two things that we do. First, I did not mention it so far, but you have to deal, I hope to have the time later to explain why you have to deal in this problem with non-integral structures, in other words, non-integral in the sense of Frobenius. So here, because this had not been done so far in the field, we have to derive a formalism for these non-integral structures. And finally, this is the work where we deal with all the wave estimates, and in particular the decay of the Tucholsky scalars psi plus and psi minus. Okay, so in the remaining time, I want, which unfortunately is not too much, I want to, so I will just focus on some of the ideas of the proof. I can only scratch a little bit the surface. Hopefully, I can discuss the modulation procedure and the formalism for non-integral structures. But I first want to give you somehow in one picture a glimpse maybe of what's happening. So let me explain this picture. So first of all, let me mention that we are in the context. The proof is in fact in the context of what is called usually a bootstrap proof, or a continuity argument. So the idea is that you're not going to immediately show that your solution is global and converges to Kerr. What you want to do is actually start with a small piece of spacetime, a small Lorentzian manifold, with some bounds which are consistent with the convergence result, with the asymptotic stability. And then you're going, so for small time, it's going to be obvious that this exists. And then you want to go to the maximal time for which these bounds are true. And you want to contradict that the maximal time is finite, therefore the maximal time is infinite, and all your good bounds are true, and you get convergence in the limit. Okay, so which means that in this proof, you never work with an infinite spacetime. You only work with a finite Lorentzian manifold, and this is what I want to show you here. I want to show you the manifold with which we work with, and this manifold, because it's finite, it has to stop at the last hypersurface, which I'm going to call the last slice, because I'm slicing my spacetime. And this last slice, you should imagine that it's a hypersurface, so it's a three-dimensional manifold, and it comes together with cuts, and the cuts are two spheres. So it's foliated by a collection by two spheres, which are, of course, they are not round spheres, they are topological two spheres, right? It's two surfaces with the topology of the spheres, and they come with these two spheres, these special two spheres, and these two spheres, you can use them to initialize outgoing null cones. So here I'm putting null codes in quote because they is not. So here, sorry, I should have reminded, I'm still using this picture, which now is a big abuse of notations because I'm not strictly symmetric anymore. I don't have any symmetries, but I'm still going to imagine that R is here, T is here, and any point now is a general two-sphere, not a round two-sphere. Okay, so I initialize the light cones from the spheres on my last slice. They stop, I stop at a fixed R constant slice, and this gives me, again, foliation by spheres here, which I will use to initialize the ingoing cones. And of course, you may wonder why I switch from outgoing cones to ingoing cones. This is because outgoing cones can never reach the event horizon, precisely because of its properties. So if you want to reach the event horizon, in fact, go slightly inside it, you will have to change coordinates if you want, in some sense, and use ingoing cones instead of outgoing cones. Okay, and then you stop at a value of fixed R, which is right beyond the event horizon. And the reason why you want to go slightly inside the black hole is because this event horizon is a very unstable hypersurface. So I want to avoid touching it. Okay, but nevertheless, so the only important thing here to understand is that the entire construction starts from this last slice. So all my choices are done on this hypersurface, which I call my last slice. And therefore, this is exactly there that you will track the final states of evolution. In other words, if you make poor choices on this last slice, you will not see convergence to Kerr. Even though your solution converges, you will not be able to see it because you choose the wrong coordinate system. You have to choose the correct coordinate system that captures convergence to Kerr, and therefore these are the choices that you're going to make here, and this is what is related to modulation. Okay, so and you do it, of course, on the last slice because this is the one most towards the future. The future is here, so this is where you can hope to capture the final parameter of evolution. Okay, so now let me maybe try to, so I'll try to finish this talk by mentioning precisely this modulation, which is related to this last slice, and hopefully, if I still have a few minutes, I can discuss the non-integrability. Okay, so here I want to focus on the modulation procedure, which I recall is the main part is the one due to general covariance. It's a modulation procedure in infinite dimension. And what it corresponds to is I want to track the final angular momentum, the final mass, and the final diffeomorphism in which I will recognize convergence to Kerr. And because the modulation in infinite dimension is more important, I will start with it. So this should start always with dealing first with modulation in infinite dimensions, which means fixing your correct coordinate system to find convergence to Kerr. So here what I want to do, so here you always want to understand something about the final state, about the final Kerr. And what I want to remember about Kerr is that in the coordinate system I showed Kerr, there were coordinates tr, theta, phi, and here I'm interested in the topological two spheres. These are not round spheres, these are only, generalized two spheres, which correspond to constant t and constant r slice. And this is a two-parameter family of spheres in Boyer-Lindquist coordinates for Kerr. And what I want to do in perturbations of Kerr is I want to find a family of spheres which correctly approximates these spheres for the end state. Okay? So this is the main building block, which is joint work with Sergio Kleinman. We precisely designed a procedure to construct a unique two-parameter family of preferred codimension two surfaces in perturbations, in general perturbations of Kerr. Okay, so here the important thing in this statement, of course, is the existence, but more importantly is the uniqueness, is the fact that what you don't want is to find too many spheres, because then you're pretty sure that your spheres are going to be round. So here are going to be wrong, sorry. So here what is very important is that we get as many spheres as there are in the Kerr spacetime, and therefore you can have the hope that these spheres are the good approximation of your spheres in Kerr. Okay, so this procedure we call general covariant modulated procedure, or general covariant modulated spheres. General covariant because the kernel is due to general covariance, and modulated because this is modulation. And the principle is that it relies on fixing well-chosen geometric quantities to agree with their Kerr values. Okay, so here, if you want an example of geometric quantities, for instance, it's a codimension two surface, so there will be two second frontal forms. So basically, you want to choose the two mean curvatures to be whatever value you have in Kerr. And there is a third quantity called the mass aspect, which is also natural, but it doesn't matter if you're not familiar with it. The important thing here is not so much the definition, because, of course, the definition is important, but it's easy to define. What is difficult is actually to show that these spheres really exist in your perturbation of Kerr, and more importantly, to get this uniqueness statement and also the fact that if you control the ambient geometry, then you control these spheres as well. Okay, once this is done, you can think as having completed the modulation scheme due to the kernel of general covariance, so the infinite dimensional kernel, and then you can move to the other parameters, which are the mass and the final mass and final angular momentum. So here, what I want to do is once these spheres are found, I want to be able, on each of these spheres, I want to define an intrinsic definition of mass and angular momentum. So for the mass, it's easy because there is a very good definition in the literature called the Hawking mass. So this was not a difficulty. The difficulty comes with the angular momentum because there were many definitions in the literature, and it turns out that none of them were working for us. So we came with yet another definition. And for the same price, in fact, you have to do something else. You have to track the final axis. You have a general Kerr solution, so there are no symmetries in your space-time. But of course, as you converge to Kerr, there will be a final axis of symmetry for your Kerr solution. So you want to track what will converge to the final axis. And it turns out that, in fact, to be able to define the angular momentum, at the same time, you have to track what is the final axis. And this we do using an effective version of the uniformization theorem that we derive in a joint work with Sergio Kleiner. Ok, est-ce que j'ai encore 5 minutes ou ça va? Ok, ça marche. Okay, sorry. So this was the issue of modulation, and maybe I will finish by discussing this issue of non-integrability that I mentioned. Okay, so maybe let me. Okay, so first of all, let me say a bit more about our gauge choices. We work in the Cartan formalism of moving frames, but instead of using the standard Cartan formalism with orthonormal frames, in Lorentzian geometry, it's more natural to use so-called null frames. So maybe let me first explain what are null frames by simply giving you the picture in Minkowski, which is very simple. So in Minkowski, so my null frames consist of a null pair. In other words, I want to give myself two null vectors in my space-time. So let me call them E4 and E3. And let me explain what happens in Minkowski. So in Minkowski, you would have two null frames, E4, which is dt plus dr, E3, which is dt minus dr in spherical coordinates. And in fact, as you can see, they are simply the generators of ingoing and outgoing null cones in Minkowski. So E4 is generator of outgoing null cones, E3 generator of ingoing null cones, and of course, these null cones, they intersect on round spheres in Minkowski. And in fact, the round sphere, the tangent space of the round spheres is simply spanned by the horizontal bundle, which is given as the orthogonal space to E3 and E4. So this is the picture in Minkowski, and this is what I want to reproduce first in Kerr and then in perturbations of Kerr. So what's happening is that in Kerr, of course, well, first of all, there are infinitely many choices of E3 and E4, but of course, as you can imagine, only a very specific one is relevant. Okay? And the one that is relevant is known in the literature as the principal null directions, and it's very important because in some sense, it diagonalizes the Riemann-Curvature tensor of Kerr. Okay, so there is a specific formula which I'm not going to give, it's not too important here, but this specific choice diagonalizes the Riemann-Curvature tensor, and it is, of course, exactly this choice which is used by Tucholsky to find his special contractions psi plus and psi minus of the Riemann-Curvature tensor. In fact, psi plus corresponds to the maximal number of contractions with E4, and psi minus the maximum number of contractions with E3. Okay, so what happens is that see, if now I look at the horizontal bundle, which is the orthogonal space to E3 and E4, now in Kerr for the principal null frame, unfortunately, now it is non-integrable in the sense of Frobenius. In other words, the tangent, this does not span the tangent space of any manifold. Okay, so this is different from Minkowski, where it was spanning the tangent space of the round spheres. Here, it does not span the space of any manifold. And this is for us a difficulty because all gauges so far in the field since stability of Minkowski were always working with integrable frames. Okay, so this is exactly why. So now if I am in perturbation of Kerr, of course, I have to work with non-integral gauges. And this required us in this joint work with Elena Georgi and Sergio Kleinemann, first of all, to make sense of a formalism using non-integral frames. So we had to generalize the formalism used so far in the field of Christopher and Kleinemann. Then, of course, the next task is to find a geometric constructions for these non-integral gauges. And finally, the third task is to find a way to derive estimates using non-integral frames, which, well, let's say have their own sets of difficulties, exactly because of non-integrability. This induces difficulties, in particular, when you try to estimate elliptic systems of Hodge type on your spheres. Okay, I'll stop here. Thank you very much.
Thank you very much, Jérémie, for this